Hello students, let us start the class without waiting further. Today we will see the next concept in the fourth module. We are almost coming to the end of the fourth module. The concept we are going to discuss now is called Hamming bound. We have seen from the previous exercises that for error correction, the matrix HT must contain the syndrome generated so that the position of the vector error bit is located. The position of the error needs to be located in the HT. So, HT must contain a syndrome. That syndrome corresponds to the position of the error bit. Now, as the order of the syndrome is 1 cross n minus k, 2 power n minus k syndromes are possible. You can see here, this is n minus k. Order of the syndrome is 1 cross n minus k. It means 1 row and n minus k columns. Means syndrome contains n minus k number of bits. When it contains n minus k number of bits, there are 2 power n minus k syndromes possible. Please understand this. For locating the error, we want to find out the position of that syndrome in the transpose of the Hamming matrix. That syndrome must be present in the transpose of the Hamming matrix. Now, this syndrome is having a width of n minus k bits. In that case, 2 power n minus k syndrome combinations are possible. Now, all these syndromes may not be present in the transpose of the Hamming matrix. That is why we had discussed earlier that error detection and error correction need not be happening together. We had seen that the error detecting ability can be more, error correcting ability can be less, which means a syndrome is obtained, that syndrome may not be present in the transpose of the Hamming matrix or the parity check matrix. HT is also called as the parity check matrix. So, in such a case, the syndrome has to be present in the H transpose or in the parity check matrix. Its width is n minus k bits. So, 2 power n minus k syndromes are possible. But please remember, all the 2 power n minus k syndromes may not be present in the parity check matrix. Okay. So, now let us see if the small t is the number of maximum errors. Till now we have been discussing only the single bit error correction. Please remember that. Let us say if the small t is the number of maximum errors, the number of possible error patterns is summation of I equals 0 to t of nci. N is the total number of bits in the code vector and I is the particular position. So, there are totally these many error patterns possible from I equals 0 to t of nci. That means nc0 plus nc1 plus nc2, like that it goes on until t. Now, all these error patterns must be present in Hamming transposed or in the parity check matrix that is available in the receiver. If small t is the number of maximum errors, then the total number of error patterns is summation of I equals to 0 to t of nci. And all these error patterns must be present in parity check matrix for the requirement of error correction. Now, we can see a relationship between the number of possible error patterns and the number of syndromes that are possible. So, proceeding further, we have this expression now. So, 2 power n minus k must be greater than or equal to summation of I equals 0 to t of nci. 2 power n minus k combinations of syndromes are possible, and the possibility of number of error patterns. You can see here the total number of possible error patterns is given by this summation, and 2 power n minus 6 is the total number of syndromes. So this 2 power n minus k has to be either greater than or equal to the total number of error patterns that are possible, where we have taken the small t as the number of errors. Now this is called as Hamming bound. Means we know that naturally we will have more number of syndromes, but all the syndromes may not be present in the parity check matrix at the receiver. At the same time, if all the syndromes are present, then the number of bits which we are going to correct, that is this total combination of error patterns. It must be equal to the number of syndromes that are available in the parity check matrix. Of course, in the parity check matrix, there may be less number of syndromes, where more number of syndromes may be possible, then naturally it is greater. So this is the Hamming bound, where 2 power n minus k must be greater than or equal to summation of I equals 0 to t of nci. Now this condition is called as Hamming bound. Now how is it stated? Let us see the statement of this Hamming bound. If an n comma k linear block code is to be capable of correcting up to t errors, then the total number of syndromes shall not be less than the total number of error patterns. The codes which satisfy this condition are called as perfect codes. Till now, in whichever example we have worked out all this error detection and correction, actually they are all perfect codes, because this condition was met with all of them. Later I will show you those examples. We were correcting only a single bit error till now. So that means we were detecting one error, we were correcting that one error. So that way, whatever error detection was happening, the same error correction was happening in all our previous examples. So they are all perfect codes only. So if an n comma k linear block code is to be capable of correcting up to t errors, then the total number of syndromes shall not be less than the total number of error patterns. If the total number of syndromes are less than the total number of error patterns, then we have a serious problem. Let us say we want to correct 2-bit errors, whereas those many syndromes may not be present at all. Then we have a serious issue there. So this is called as Hamming bound. 2 power n minus k must be greater than or equal to summation of I equals 0 to t of nci. Let us see the examples now. For the 7,4 code with t equals 1 for a single bit error correction, we have summation of I equals 0 to 1 of 7ci. That is 7c0 plus 7c1, that is 1 plus 7 is equal to 8. And we have 2 power n minus k is 2 power 7 minus 4 is 2 power 3 equals 8. Now here you can see 8 is equal to 8. That means the Hamming bound is satisfied here. This particular code is now a perfect code. Now even for the 7,3 code, which we had worked out a lot of examples, even for the 7,3 code, 2 power 7 minus 3 equals 2 power 4 equals 16, that is greater than 8. Because our first condition remains the same. Summation of I equals 0 to 1 of 7ci. N is 7 there. We are correcting one bit error. The t is 1 only. So it is 8 only. In the case of 7,3 code also, we are getting 2 power n minus k is 16. 16 is greater than 8. Hence 7,3 code is also a perfect code. So we have been dealing with the perfect code only till now on these examples. Whichever code is not satisfying this Hamming bound is an imperfect code, which means its capability of error detection and error correction is seriously under threat. So as much as possible we have to deal with perfect codes only. The way to check the perfection of a code is only to check that whether the n comma k and t together whether they satisfy the Hamming bound or not. Any code that satisfies that Hamming bound is called as a perfect code, and we will have to work with only the perfect codes. We should not have imperfect codes in our information theory as such. Otherwise, we are going to make a compromise in the quality of the error detection and correction. Now, that is the concept of Hamming bound. Let me proceed further. We are coming to the end of this fourth module now. I will go a little faster now because this is a very simple topic now. I need not go into so much of elaboration for this particular methodology which I am going to discuss now. We have a method called table lookup decoding using standard array. Here, is it required that at the receiver it should keep on generating all types of syndromes every time when a code vector is received? Or can it have all the syndromes that are possible can be stored in a memory, and whenever required it can simply refer to the table instead of always computing the syndrome? So that is this method called table lookup decoding using standard array, which means we can have a lookup table for all the syndromes that are possible to be generated with the particular scheme of n comma k. So at the receiver side, the computation of h and s equals RH transposed requires a large computation effort. We need to have a Hamming matrix at the transmitter, that is anyhow obvious. At the receiver also the same Hamming matrix is required, and we have to compute syndrome for each received vector. That requires a large computation effort. In the exams which we have worked out, it is not so much effortful because we have been dealing with only 7-bit code vectors and with the 3 check bits. There is no large computation. But think about if we deal with 32 bits and 64 bits and 128 bits as the total width of the code vector, think about the matrix operations that are to be performed at the receiver. That consumes sufficient amount of time as far as the CPU is concerned. Now, to make the decoding faster, the receiver can adopt a table lookup decoding approach. Instead of computing this S equals R into H transposed every time, the decoding can be faster now by going for a table lookup decoding approach, in which all the valid code vectors are stored in a standard table. That is the idea. All the valid code vectors are stored in a standard array, and in addition, all the possible received vectors with the 1-bit error are also stored in the same array. Means, let us say we are going for a 1-bit correction only at the receiver, then all the possible vectors which will have 1-bit error, they also can be stored in the same array, and corresponding to all those vectors which are having an error, corresponding syndrome also can be stored in the same array. Now, there is no need to compute the syndrome every time. Corresponding to a received particular code vector with an error, corresponding syndrome can be easily found out in the table. So, whenever a vector is received, the receiver will search for the same in the standard array and obtain the corrected code from the table itself without performing the large computations. As soon as the syndrome is obtained for a given code vector, automatically the code can be immediately corrected. The received code can be immediately corrected without performing the large computations. Now, this is the advantage of table lookup. Now, what is the disadvantage? All these have to be stored in the memory at the receiver by default always. So, the requirement here is that all the possible vectors must be stored in the array. Hence, this requires a large amount of memory. In the earlier case, memory requirement was less, whereas computation effort was more, or the CPU time was consumed. Now, in this case, the CPU time is reduced, but the memory is required at the receiver as a larger amount to store it in the tabular format. The advantage is the faster decoding process. As you already know, if you have to gain something, we will have to be ready to lose something else. So here, if you have to gain a larger processing time, larger decoding time, then we will have to lose upon the cost of the large amount of memory. Now, for example, a 6,3 linear block code has 2 power 3 equals 8 code words, and it has 6 minus 3 equals 3-bit syndrome vectors. Now, the 3-bit syndrome vectors are totally 6. Hence, all the syndromes are stored in the first column of the standard array, and all the valid code vectors are stored in the first row. Now, all the syndrome vectors are also stored, all the possible error vectors are also stored as R equals C XOR E. All the other columns are stored with the vectors with 1-bit error, which corresponds to the syndrome in the particular row. Now, for the 6,3 code, the first element, the first row of the standard array is 0, 0, 0, which corresponds to null syndrome. Hence, later the first row contains all the valid code words. Later in the first column, as the 6 syndrome vectors are stored, the received vectors to be stored are 6 into 8 equals 48. All these vectors will have their corresponding syndromes in the first column, and hence the corresponding code vectors will be present at the top in the respective column. Now, the method is shown below here. Whatever I discussed till now is the method shown. You can see a column is there for a syndrome, and there is something called coset leader along with the, let us say, a code word and the error vectors. You can see another code word along with the error vector. That word can go on from CA, CB, CC up to C2 power K. Now, this can contain the syndrome and all the other columns. It is called as a coset leader. Using that coset along with the error vectors, correction can be possible immediately. You can see that here. Now, here the syndrome SCA corresponds to null vector, and hence CA also is a null vector. The very first syndrome is 0, 0, 0. So, naturally the coset leader is all code vectors only. But later on, the syndrome will be having any position of filled by 1. It need not be 0, 0, 0 later on. So, naturally the other coset leaders will be having a different pattern there. You can see here EB and EB XORed with CB, EB XORed with CC, that way it can go on. Now, EB is the particular error vector. This way we can fill this table along with the basic code words at the top and along with the corrected code vectors at the other positions of this particular table. So, this table completely contains the code words without the error and the code words with all 1-bit errors. This way the table can be populated. So, that is why EA is absent in the table. EB till EN are the error vectors corresponding to the syndromes. Now, for a n, k linear block code, there are 2 power k code vectors and n syndromes, excluding the SCA, the very first one. Hence, the number of error vectors is n excluding EA, that is n minus 1. The set of all error vectors is called as the coset. The set of all error vectors is called as the coset, and the first n tuple of each coset is called as the coset leader, as I had shown in the table earlier. The standard array thus formed has now the following properties. Each element in the standard array is distinct. We have SCA, SB, SC, like that goes on. In the first row we have CA, CB, CC. Later on we have that EB XORed with the CA, and it goes on. So, each element in the standard array is distinct. If the error pattern does not match with the coset leader, then the decoding will be incorrect. And all the 2 power k n tuples of a coset have the same syndrome, because for that particular bit position error, all the cosets will have the same syndrome. Now, the second point, please observe that if the error pattern does not match with the coset leader, then the decoding will be incorrect. which means what? That E XORed with C, if that error is not matching with the coset letter, decoding will be incorrect. So we should take care to populate this table such that all the 1-bit error patterns are addressed there, which means all the cosets contain the all possible 1-bit error patterns, otherwise the decoding will be incorrect. So you can observe, this is because of, if let us say we take care of only a single bit error detection and correction, then populating this table will be really easier. If at all we have 2-bit error detection and correction, then the table will be much larger, much enormous in size. That is where it consumes larger amount of memory at the receiver. But that is the price which we have to pay for saving the time there. Okay, with this I have come to the end of the 4th module. Now let me start the 5th module. It is chapter 5 or module 5, that is called binary cyclic codes. Till now we have been discussing linear block codes and how we had defined the block codes. A block is going to contain a set of data bits and a set of check bits. Please recall that. And the check bits can be either in the beginning or at the end of the block. And in all our examples, we had considered the check bits at the end of the block. And that was a systematic block code. Now, what are the disadvantages of these block codes? There are these matrix calculations. And all the matrix calculations are cumbersome. In the sense, if at all you go for block codes only, both at the transmitter and at the receiver, we have to reserve lot of memory space for storage as in the matrix form. And later on, we will have matrix multiplications using the modulo 2 arithmetic. So that is going to have sufficient computation effort. So the matrix calculations are cumbersome, even though there is advantage there. There is a heavy advantage there, but we are paying the price for this memory requirement. Next, encoding and syndrome calculation circuits are much complex for larger vectors. We had dealt with only 7,3. Now think about 32 and 64 and 128 bits. Now even the encoding hardware is a much larger hardware. Even the syndrome calculation hardware is a much larger hardware. It is much more complex. Because if you recall the basics of HDL, whatever you have studied earlier in the second year, you have already become familiar with the concept called combinational circuits and sequential circuits. Now you know that all the combinational circuits are concurrent executions, which means for all the combinational circuits, there is no time delay in the processing except for the propagation delay. There is no other delay as such. That means all combinational circuits are of concurrent nature. They process all the input bits simultaneously. Unless in the sequential circuits where a bit is taken and as per the clock's edge, a decision is taken. In general, sequential circuits work in the serial fashion. Combinational circuits work in the parallel fashion. So now when we have all these matrix calculations and we have encoding and syndrome calculation circuits, which we have dealt with as combinational circuits with a lot of XOR gates and along with the registers for initial storage of the bits. Now we know that whichever hardware is working concurrently or parallelly, that is going to be much bigger and cumbersome and complex. How to solve this problem? For solving the problem, instead of going for a concurrent execution, we go for a serial execution, which means we break up a parallel number of bits into serial one by one, and we can handle bit after bit. That is why now this is called as cyclic code. Please recall that always we have the choice of making the system as concurrent or sequential. For example, a microprocessor or a microcontroller is concurrent as far as the data bus and the memory is concerned, as far as the internal memory is concerned. Now the memory can be 32 bits wide and the CPU or the microcontroller can have the data bus width of 32 bits. Now the data exchange can happen in between the memory and the processor concurrently for all the 32 bits. That is the power of concurrent execution. Now think about a peripheral. A peripheral is going to have a serial data and that data comes one after the other. Now CPU will communicate with the peripheral. For example, USB bus itself is there, universal serial bus is there. That USB is basically a peripheral connectivity to the pen drive or to the keyboard or to the mouse or to any other such peripheral equipment or device. In that case, the data is going to come one after the other. When the data is going to come one after the other, CPU will handle those bits one after the other, where time taken is more, but memory requirement and computation is less because bit after bit is coming. That way each have their own advantage, each have their own disadvantage. In case of combinational circuits or concurrent execution, we are paying a higher price for the computation as well as for the hardware requirement, but it is faster. In case of a sequential circuit or a serial execution, we are saving the cost of larger computational effort and the memory, but we are paying the price for the speed now. Now, whatever I discussed till now was applicable to the linear block codes, where the hardware was basically of concurrent nature, combinational type. From now on, we are going to deal with the cyclic codes, where we will overcome these two disadvantages of the block codes, but they will have further disadvantage now because the speed is going to be reduced, but obviously. So the two limitations of the block codes are overcome by means of the binary cyclic codes now. Now these codes have the following advantages. The cyclic codes have the following two advantages. They are represented using polynomials now. Instead of n, k code in the linear block code, we had represented in terms of check bits and the data bits, and we used matrices for their computation. Here in the cyclic codes, we are representing the codes using polynomials, not using exactly the matrices. That way computation is reduced. And then encoding and syndrome calculation circuits are implemented using shift registers only, not using those concurrent or combinational hardware. Of course, there also we had a register for storage of the bits in the beginning. Later it was all using XOR gates because of the modulo 2 arithmetic. Here we are going to implement them only using shift registers. Why? We are going to represent the code using polynomials. We will see how we are going to use polynomials for these codes gradually in today's class and in the future classes. So let me proceed now for the discussion of the cyclic codes. Now the definition. A n, k linear block code is said to be cyclic code. See, we discussed the linear block code in the beginning so that from the linear block code only we will derive the cyclic code. That is how we define a cyclic code in terms of the linear block code only. For example, when we now have the electronic hardware in which a lot of serial communication is happening, the serial hardware was derived again from the parallel hardware only, which means the sequential logic was derived again from the combinational logic only. In the beginning, it was combinational logics only. All the logic gates which we use in electronics are basically combination logics, and they are all of concurrent execution only. Now when you connect the combination logic along with the memory element, then you make it as sequential. Please recall all the basics of HDL now. So now, as we had derived the sequential elements by using a combinational elements, in the same way, we are going to derive the cyclic codes in terms of the linear block codes only. So n, k linear block code is said to be a cyclic code if every cyclic shift results in a code vector. That is the beauty here now. In the case of a linear block code, we used to derive that particular code vector with respect to a particular data vector with the particular relationship. We had a matrix called Hamming matrix, and the Hamming matrix contained a parity matrix there. Please recall all those basics which we discussed earlier. Okay. Now, here instead of the matrix, what we do is we simply shift the code itself. Now you can see if CA is 0 1 1 1 0 0 1, then let us go for a shift here now. You can see the shift here. This is shifted here now. When this 1 is shifted here, you will see this code now. 1 0 1 1 1 0 0. See this? We have two distinct code vectors now. Now you may wonder, if this is happening, where are the data bits, where are the check bits? Right now don't worry, because we are going to represent this code in terms of a polynomial. The data bits also will be there, the check bits also will be there. Only thing is, they will not be as systematic as the earlier code. Our idea is that we will have to reduce the computation effort here. So we will purposefully go for some other tricks here. That's why I had told, always we had a initial concurrent execution, later on we went for a sequential execution. Always we had an initial combination logic, later on we went for a sequential logic for saving the resources. Same way here, if let us say a code vector is 0 1 1 1 0 0 1, now with the shift it becomes another code vector 1 0 1 1 1 0 0, another code vector with the further shift. Now let us say this is shifted here. This will result in 0 1 0 1 1 1 0. Same way it goes on. Let us say one more shift here. That's going to result in 0 0 1 0 1 1 1. Similarly, you can see 1 0 0 1 0 1 1 1 1 0 0 1 0 1. Finally 1 1 1 0 0 1 0. Finally, if at all you have this shift again, this will result in this code only. You can see this. If a shift happens with CG, then it is 0 1 1 1 0 0 1. This way, simply a cyclic shift is going to result in these many code vectors without any specific bigger algorithm. So you can see we have now 7 code vectors which are derived so easily. We have only one fundamental code vector here. You can see this is the fundamental code vector, and this vector results in the other code vectors. But the intelligence here is we have to choose a fundamental code vector which will result in other code vectors. That is the ingenuity here. If the fundamental code vector does not have a particular representation or a polynomial, then the other code vectors may not be having that variety. Other code vectors may not be having the ability. That is where the choice of the fundamental code vector is important here. And every shift will result in a different code word. That is why this is called a cyclic code. Why? Because we are simply rotating the code word. It is simply a shifting, cyclic shifting. Now this is easy. By using only shift registers, it is simply possible to generate all the code vectors at the transmitter also. It is easy now. So this means that we will have those many code vectors as many bits are there in the code word for the particular choice of the code vector. You can see here, we have these 7 bits now. For the 7 bits, we will have distinctly 7 different code vectors. Now, in addition, all the code words can be represented as polynomials. Now, let us see how to represent these code words as polynomials. Now, you can see here. See, now the CA is 0111001. Now, let us say, I'll just write here only. Let us say, I will represent this as, let us say, 1. Then I'll represent this as x. Then I'll represent the other position as x squared. Then x cubed, x power 4, x power 5, x power 6. Imagine we are going for a crude scheme of representation, where let us say the very first position is simply as 1. Next position as x. Next position as x square, x cubed, x power 4, x power 5, x power 6. If that is the general representation, now I can represent the CA as a polynomial. Let me change the color. Now I can simply write CA as 1. 1 is not there. See, 1 is not there, because the first position is 0. Next one as x. Let me stop annotating. Let me write it neatly now. Now I can write it. The first position is not there. Next position x is there. Next position x square is there. Next position x cube also is there. And last position x power 6 is there. You can see x is there, x power 2 is there, x power 3 is there, x power 4 is not there, x power 5 is not there, x power 6 is there. So I can simply represent the CA as x plus x square plus x cube plus x power 6. Remember that plus is again a symbol there. It is not an addition there. In information theory, you should remember that plus sign is simply a notation there. So I can simply represent CA as x plus x square plus x cube plus x power 6, which indicates that in those 4 positions, the bit is 1. In all other positions, the bit is 0. That way, I can simply write CA as x plus x square plus x cube plus x power 6. Now, this is a polynomial representation of the first code. Similarly, for the second code, we can represent 1 plus x square plus x cube plus x power 4. See here, for the second code, CB, now we can write, as the very first bit is 1, we can write 1. Then, second bit x is not there, third bit x square is there. So, we can write 1 plus x square. Then plus fourth bit is x cubed, because it is associated with the term x cubed, plus first one, second one, third one, fourth one, fifth one, that is x power 4. So now 1 plus x squared plus x cubed plus x power 4, that is going to be the representation of CB in polynomial. So this way we can represent all the codes, all the code vectors that are possible. In our example, it was 7-bit code vector. So 7 code words are possible. All the 7 code words can be represented using this polynomial. Now, how to use this polynomial in our future error detection and correction methodologies? We will have to go for polynomial multiplication now, polynomial division now. Just like we had gone for matrix multiplication there in the linear block code. Of course, we did not seriously perform any matrix division there, because we had represented the syndrome vector as in terms of the parity check matrix, S equals R into H transposed. Using that, we used to easily find out the syndromes. We did not go for matrix division seriously there in our earlier teaching learning activities. Now here we will have to go for polynomial multiplication, polynomial division, because we are representing these code vectors in terms of such polynomials. So let us see an example of how to multiply this polynomial using this modulo 2 algebra. Please remember here that plus means modulo 2 or XOR operation. So now let us multiply these two polynomials. Remember, these two polynomials are nothing but two code vectors now. 1 plus x square, 1 plus x square into 1 plus x cubed plus x power 4. Let us multiply that using modulo 2 algebra. Now 1 into 1 is 1, and then 1 plus x cube plus x power 4 directly, then x into 1 is x, so x into 1, x plus x squared plus x power 4 plus x power 5. You can see here x plus x squared plus x power 4 plus x power 5. Lastly, when x squared is multiplied into this polynomial, we get here x squared plus x cubed plus x power 5 plus x power 6. Now we can separate all the common terms. 1 plus, then x we have here 1. Let me annotate. We have x here and x here. So it is x into 1 plus 1. Similarly for x squared, we have x squared here and we have x squared here. That is again x squared into 1 plus 1. Again for x cubed, we have here x cubed and x cubed. That is again 1 plus 1. X power 4 also we have here and we have here. That is again 1 plus 1. X power 5 also we have here and then we have here. So that is again 1 plus 1. You know that 1 XOR 1 is always 0. We are going for modulo 2 algebra. So that 1 plus 1 in modulo 2 is 0. So all these terms become 0. And we finally arrive at 1 plus x power 6. Now this is the resulting polynomial for the polynomial multiplication of these two. Now look at this. What is this now? This is now 1, 1, 1, 0, 0, 0, 0. This is now 1, 1, 1, 0, 0, 0, 0. What is this now? This is now 1, 1, 0, and then 1, then 1, then 0, then 0. I am writing the binary pattern corresponding to the polynomial now. You have 1 plus x square, that is 1, 1, 1, 0, 0, 0, 0. This is 0. You will have to clearly understand this is 0. I am writing through a mouse, so it has become some shape. It is 0. Again 1 plus x square is not there, it is 0. X cube x power 4 is there, 1, 1, that is 0, 0. Now when you multiply these two vectors in the modulo 2 algebra, you will get the output as 1, 0, 0, 0, 0, and then 0, then 1. This may seem like crazy, but it is done using modulo 2 algebra. Okay, so the resultant